Here we're going to prove the second theorem, the second Hohenberg-Kohn theorem. Let me remind you which was that second theorem. A universal functional for the energy, E, which depends on the electronic density, in terms of the electronic density, can be defined for any external potential. And the exact ground state energy of the system is a global minimum, and the density that minimizes this functional here is the exact ground state density. Okay, so that's basically we are saying that in this Theorem II that we can define the energy functional and we can apply the variational principle in terms of the density to get either the ground state energy and the ground state electronic density. So the proof of Hohenberg-Kohn theorem and the proof that I developed, it's going to be very simple. It's restricted to densities, to electronic densities that are ground states densities of the electronic Hamiltonian with some external potentials. And that densities, they're called V-representable densities. This defines a space of possible densities within which we can construct functionals of the density. So how we are going to derive that proof? That's actually going to be really simple. So considering the first theorem, we just proved that all the properties of the system, such as the kinetic energy, potential energy, everything, are uniquely determined if the electronic density is specified. Then, therefore, considering that, each such property can be viewed as a functional of the electronic density, of course including the total energy. So we can have a functional of a total energy, and the function is going to be something like that. So the function of the total energy is of course going to depend on the electronic density. We'll have a term that will be a function of the kinetic energy, that of course is going to depend on the electronic density. Then we have another contribution which is going to give the electron-electron interaction, which can be seen as another function of the electronic density. And then we have an additional, a third term. It's going to give a term associated with external potential, where the functional, as you can see, it's very simple. We know which is this functional in terms of the electronic density. These two functions, in principle, we don't know, but we're going to collect the contribution of these two first in one functional we are going to call F. That's going to be the functional which includes the electronic kinetic contribution and the electron-electron interaction. And this functional here, the one that does not include this external potential, this one must be universal in the sense that it should be the same for all electron systems, independent of the external potential, because it has no contribution associated with external potential. That the contribution associated with external potential is coming here. And of course, we can define that function. This function is going to be just the sum of these two functionals, the kinetic energy and the electron-electron potential, because both are functionals of the electronic densities. So once we have that functional, then we can apply the variational principle in order to get the ground state density and the ground state energy. So how is that? Consider a system with the ground state density N1. Okay, we have this ground state density corresponding to the external potential 1, Vx1. Okay, then according to that, the ground state energy, if we have that the ground state wave function of the system is Ψ1 and the density associated to that ground state wave function, it will be therefore N1, then we have the ground state energy is just basically this contribution here, where H1 is the Hamiltonian, including that external potential we have called Vx1. Okay, this is the ground state energy. That considering that we have just defined a functional of the total energy of the system in terms of the electronic density. If in that functional we substitute the density with the ground state density we have called N1, then we should have the ground state energy. Okay, that's what we have. Now consider a different density which we are going to call N2. That, of course, corresponds necessarily to a different wave function we are going to call Psi2. It follows that the energy associated to that state, Psi2, it should be higher than E1. Why is that? That's the direct consequence of the variational principle. This is the energy we have called E2, which is the energy associated to that state Psi2. So basically it's the average of the Hamiltonian H1 corresponding to the state Psi2. But according to the variational principle, that one should be should be higher than the ground state energy, which is E1. So therefore we have that E1 should be lower than E2. So what does it mean? It means that the energy associated to the density N1, so if in the functional if we substitute the density with the ground state density, so therefore this term, which basically is the ground state energy, it's going to be lower than the value that we can have for this expression for any other density. So if in the functional we substitute the density with N2, for example, so we will get E2, therefore, this value, it should be lower than this one. It's something trivial. So according to that, knowing that functional, we can minimize that with respect to the electronic density, and that density that minimizes that functional will be the ground state density. And the energy associated to that ground state density will be the ground state energy. So in case of knowing that functional, even though, however, we don't know which is this functional, in case of knowing, if we had that functional, we could minimize that in order to have ground state energy and ground state density.